Greetings and welcome once again to my new calculus channel. My name is John Gabriel. So, um, you've heard a lot about the elements. A lot of uh, incredibly stupid fools, such as math professors and researchers, have talked about the elements. Of course, the nincompoops never understood what the elements were about. They never understood what Euclid was trying to do. And they still don't know up till this very day what the elements are about. And no, they're not about geometry. They're not about any of the drivel that you hear those incorrigibly stupid idiots of mainstream mathematics telling you, okay? So now, let me begin. The word measure appears hundreds of times in the elements, okay? Hundreds of times. So, what does the original Greek word for measure mean? Okay, so, well, there are several words. For example, metρήσει means measure, and so does metro, but metro is a measure, so it's a noun, right? And this word metρήσει that you see here appears it appears 213 times. But it's not the only form of measure. For example, if you put omega in there, and we can get an omega from here. So let's just put an omega there and copy that. So if we put omega here, we see also that there are 62 of those, right? Symmetron, by the way, means measure in this case, okay? Or same measure, it means same measure. And asymmetron means no same measure. So again, that word, and it appears also as metro. So if we go back to the beginning of the elements, these are the original Greek elements. Let's go to the beginning and say this and say that. Okay. And so here, again, don't know why it took me this far, but I guess it's continuing where it left off. So in any case, the word metro does appear, and it means noun. And anytime it appears in symmetron or asymmetron, it also is referring to measure. Okay, so how did the Greeks understand measure? How did the Greeks understand measure? All right, so the most primitive operator which they dealt with was the one of difference. So they would have two line segments, and they would want to know the difference, which is this part here, right? And that would be very easy to get. All you do is you copy this with a divider, put it on like that, and then you take your divider and you do that, and you have the difference. Okay? So that's what the difference is. And now addition is defined in terms of subtraction, or the sum is defined in terms of difference. So when you say, for example, 1 minus minus 1, you're removing the need for 1, okay? You're removing the need for 1. And this is the same as saying 1 plus 1, but it's still defined in terms of the uh, subtraction or difference operator. However, you cannot define the addition. You cannot define the subtraction operator in terms of addition. So, for example, you cannot say something plus something like that, whatever, where this is defined in terms of, uh, I'm sorry, this minus this, where this is defined in terms of addition. Okay, so you can define sum in terms of difference, but you cannot define difference in terms of sum. So difference is the most primitive operator, okay? Then you have sum, okay? So difference tells you the part that they're different, and geometrically, you know 100% what difference is, like I show you here. But what does sum mean? Well, sum is also a measure, But it's not a difference measure exactly. It's indirectly a different measure. It is a measure that tells you that if you have two operands like that, that both of them measure the sum exactly. Okay, so if you took that one and put it there and that one and you put it there, that's what sum means. Okay, so you could have this one and you remove the need for this one. Okay, remove the need for this one, and then you'd have the whole line. All right, so difference and sum are the two uh, primary arithmetic operators, with difference being the most primitive because you cannot define difference from sum, but you can define sum from difference. All right, so now somebody asked some time ago about this diagram I had in here where I was demonstrating the concept of division and subtraction. So the next thing that comes after difference and sum is division. And of course, division can be defined in terms of either of these two, okay? So say, for example, you have a line like this, and you have a line like this, right? Then you can say that the measure of this line here, let's pretend that these are equal, okay? The measure of this line here is when you take this line segment, measure that part, and you measure that part, and you measure it in an additive method. So you start here, you measure it like this, and then you measure this part. Now, if you were doing the difference method, you would take this same uh, uh, measuring tool, and you'd cross that out, and you'd write a 1. Then you'd cross that out, and you'd write a 2. But it has the same effect, right? Whether it's subtraction or addition. So, so division is a measure, and what it does is it measures the one magnitude with the other. Okay, so if you have, let's say, 6, and you want to measure it with 2, right? You can say it's 2 plus 2 plus 2, right? 3 times. Or you can say it's 6 minus 2 minus 2 minus 2. You can measure it in either of these two ways. Doesn't matter which one you use. Of course, difference is the most primitive. And then, of course, immediately after it is addition. So what does division and multiplication mean? What exactly are those measures? Now, what did I do here? I didn't mean to do that. What exactly are those measures? Let's see. Now, say, for example, you have 6 divided by 2, right? You could write that as 6 over 2. Or if you wanted to simplify it, you could say that's the same as what? It's the same as what? It's the same as 6 over 2. And you would say minus 3 minus 1, right? That would equal to 3 over 1. Does that make sense? Or you could basically find a fraction that is in proportion to this and just continually subtract the numerator from the top and the denominator from the top and the denominator from the bottom. This here is simplified in book or exemplified rather in book 5, proposition 12, from which all the operations are defined. So what does it mean if you say, for example, 2 times 3? Okay, so we know 2 divided by 3 is just 2 over 3, right? That's the result. There's no more division pending there. It's finished. That's the number. What does 2 divided by 3 mean? Well, multiplication is a special form of division. It's a division in which we measure the 2 using the reciprocal of 3, okay? Or we measure the 3 using the reciprocal of 2, right? And if we do it this way, again, we use proposition 12 of book 5, don't we? And we can say a half plus, put a 3 there, plus a half. And whatever we do to the bottom, we do to the top, right? Like that, okay? And that gives us, since this is 1, we can stop. We don't want to go any further, we can, but we already got a 1 at the bottom. So that's 6 over 1, right? Pretty neat, isn't it? Okay, so 2 times 3 is 6 over 1. Or we can say here, this is the same as 2 over a third plus 1/3. Okay, we still don't have 1 on the bottom, so let's just add a 2 there. Let's add another third again and another 2 there. So now we have 1 on the bottom and 6 on the top. So division is multiplication is a reciprocal process of division. Okay, and that's what it means. And you don't change the method. So, for example, you don't say 2 is 2 groups of 3, or the crap that you taught in mainstream, or 3 groups of 2. It's all done the same way, using similar triangles, like I show you over here. Okay, so if you've got this proportion, 3/4 to 5/2, you can increase each side by the same amount or decrease it by the same amount. Or you could say that if you have this proportion, let's reset the canvas. If you have this proportion like that, and you draw a line linking them, then you can use any parallel line. And this section here to this section here will be the same as this section to this section. So the proportion is maintained. Okay. Now, anyone who tells you that mathematics is not about measure and number is an absolute moron. Like I showed you in the original Greek methods. Oh, here's another one again. Um, all these propositions, everything that you see, it's all a build-up to from geometry, from a qualitative measure to a quantitative measure through the abstract unit. It's all a build-up. And so what I'm going to do now is I'm going to leave you with this and put a link in the detail section called The Ultimate Book of Numbers, where you can learn about all these things and become smarter than your lecturers and those absolute idiots who call themselves mathematicians. So if you haven't already subscribed, become a subscriber, click like, become a follower on Academia. I'll place a link there. I'll also place a link to this article so you can study it. This is a very important article. You cannot call yourself a mathematician unless you understand this article. It's so important that I wrote it in both English and Greek, okay? Because, of course, my Greek distant relatives are also a bunch of morons. So, and in here I explain what all these things mean, so you can understand that if the ancient Greeks didn't or hadn't rejected 0 as a number, you wouldn't have fraction arithmetic. You wouldn't have any arithmetic. You wouldn't be able to add fractions. You wouldn't be able to do anything. All that is based on the foundations which Euclid put together in the Elements. Till next time, my name is John Gabriel, and this is a New Calculus channel. Goodbye.